Start. 6, 5, 4, 3, 2, 1, 0. All engine running. Liftoff. We have a liftoff.
The subject of my presentation is determination of global geodetic parameters using GPS, GLONASS, and Galileo satellite systems. And I'm going to divide my talk into 4 parts. Firstly, I will provide the scientific background and the motivation of my research. Then I will move on to the results and discuss the differences between global geodetic parameters from GPS, GLONASS, and Galileo, show the benefits of the combination of these 3 systems, and identify the system-specific errors in multi-GNSS solutions. Next, I will draw conclusions and outline some research ideas for future work. Global navigation satellite systems became a part of our everyday life thanks to the GPS system. However, through the last decade, many independent, global, and regional navigation satellite systems have been developed. And in fact, there are more than 130 satellites in orbit that support satellite-based navigation. And experience in satellite data processing shown us that using as many satellites as possible is in essence beneficial. However, the diversity in technical details among the different types of satellites poses a scientific challenge taken up for many years by the International GNSS Service, especially in the frame of the multi-GNSS pilot project. GNSS serves a wide range of applications, starting from positioning, navigation, and timing, through the list of other applications as listed below, to Earth observation using global geodetic parameters. And the last one is of primary concern in my research. Geodesy is a science which provides a mathematical description of the Earth with its temporal and spatial variations. And in the interdisciplinary context, the global geodetic parameters are the fingerprints for monitoring of phenomena in Earth system. In my research, I focused on 4 global geodetic parameters: station coordinates, and the global network of stations represents the Earth figure and their motion reflect the changes in the Earth crust. Satellite orbits, which provide a precise information about the satellite motion, and the accurate modeling of the satellite orbit is a prerequisite for other GNSS-based products. The term Earth rotation parameters refer to X and Y pole coordinates and length of day, and these parameters constitute transformation parameters between orbit, celestial, and station, terrestrial frames. Earth rotation is variable in time, and this variability reflects geodynamical processes. Finally, the Geocenter motion is a vector between a natural origin of the orbit and the station frame origin. Geocenter motion is variable in time and following the total mass redistribution in the Earth system, including oceans and the atmosphere. Now let's consider the main differences between the 3 systems included in my research. Both GPS and Galileo are military systems, so the technical details about the system itself and the satellites are only selectively given to the public. Galileo is fully civilian, which means that we can expect more information from the system authorities, like for example in the form of satellite metadata. Through the long experience with GPS data processing, we achieved great quality of GPS solutions. Processing GLONASS and Galileo observations still bring some new challenges, like for example ambiguity resolution and orbit modeling. This figure presents the development of the GPS, GLONASS, and Galileo constellations. And what is interesting here is that since 2019, we have more Galileo satellites in space than GLONASS satellites. And looking at the orbital characteristics of these 3 systems, GPS is distributed over 6 orbital planes, which provides good observational geometry, while GLONASS and Galileo are distributed over 3 planes, which is not perfect for Earth observation purposes. Thanks to the launch failure of 2 Galileo satellites, the nominal Galileo geometry nominal Galileo constellation is supported by an additional highly eccentric orbit, which makes the Galileo observation geometry more varied. The revolution period of the GPS satellites is in deep resonance 2-to-1 with the Earth rotation, which allows for propagation of orbital errors into Earth monitoring parameters. The orbital resonances for GLONASS and Galileo satellites are much weaker. Finally, the orbit quality achieved so far for these three systems is also different. And for GPS, the orbit modeling problems are difficult to be handled because of no support for the satellite laser ranging technique. And for GLONASS, we are aware of some issues for individual satellites, and handling non-gravitational forces is also challenging. Despite the short development time, we can deliver Galileo orbits with at least similar quality to GPS, and we can even expect further improvements thanks to satellite metadata. When discussing the differences between the systems, we should also remember that all the GNSS should be interoperable at the system level, which means that individual systems should provide the same results when used standalone, and the user should benefit from using the different systems altogether. However, this is not so straightforward. And the differences between GPS, GLONASS, and Galileo highlight the system-specific errors, while the differences that are common for all the GNSS with respect to the other satellite and space geodetic techniques then highlight the technique-specific errors. And identification of both these issues helps us with understanding GNSS technique in general and improving GNSS-based observations and making the monitoring of geodynamical phenomena in the Earth system more robust. This consideration led us to the hypothesis that the use of the Galileo system allows improving the quality of determination of fundamental global geodetic parameters, such as pole coordinates, length of day, and geocenter motion, and consequently enhances the realization of the GNSS-based terrestrial reference frames. And the two main questions arise here. What is the magnitude of differences between the geodetic parameters estimated using GPS, GLONASS, and Galileo? And what's the benefit of using multi-GNSS, including Galileo, in delivering geodetic parameters? To verify the hypothesis, I have prepared the processing chain incorporating GPS, GLONASS, and Galileo observations and processed the data using a modified version of Bernese GNSS software. My strategy is in analogy with the IGS analysis centers providing GNSS-based global parameters using double difference-based observations. And I selected the network of approximately 100 stations, all of which track GPS, GLONASS, and Galileo observations. My analysis covered up to 3 years of data starting in 2017, and to evaluate the differences in global geodetic parameters from GPS, GLONASS, and Galileo, I have used a unique feature of Bernese GNSS software, which allows to estimate these parameters as system-specific in common multi-GNSS processing. Now let's move on to the results, and I will start with Earth rotation parameters. As I said, Earth rotation is variable in time, and determination of Earth rotation parameters using satellite and space geodetic techniques depends on the selected network of stations, the quality of station coordinates, and the quality of orbit modeling. Earth rotation is variable in time, and we may distinguish low-frequency variations, as for example presented here for X and Y pole coordinates, and these are measured using satellite space geodetic techniques, including GNSS. And however, available GNSS-based solutions are dominated by GPS. And the high-frequency variations in Earth rotations are induced mostly by the ocean tides, and these are modeled in GNSS processing using external data. As for example, the model presented here is recommended by the International Earth Rotation and Reference Systems Service. And this model is recommended in the conventions from 2010 and is based on the data from satellite altimetry. However, we don't know what's the level of consistency of such models in multi-GNSS solutions. The next part of the presentation refers to 2 scientific articles which discuss the low frequency and high frequency variations in Earth rotation from GPS, GLONASS, and Galileo. However, to begin with, I will explain one aspect of our orbit modeling, which is essential in understanding the next slides and results. In GNSS, direct solar radiation pressure is the main non-gravitational force acting on the satellite, and most commonly it's handled using empirical models, such as ECOM developed by Center for Orbit Determination in Europe, which decomposes the perturbing forces acting on the satellite in 3 directions of the sun-oriented frame. We can also build a simplified model, box-wing model, of the satellite and estimate the forces acting on the satellite a priori. To that aim, we can use official information, as for example, this provided for the Galileo satellites in the form of satellite metadata. Or when no metadata are available, we can use pre-adjusted satellite properties like this, for example, provided for GPS and GLONASS satellites. The a priori box-wing model may be complemented with simplified empirical models such as, for example, the reduced set of ECOM parameters, excluding the high-order Fourier terms in the d direction. This is the so-called hybrid approach, which leads to the orbit improvement, as reported by Inter alia et al. However, we don't know what is the effect on the estimated geodetic parameters. So now let's have a look at the low frequency variations in polar motion from single system solutions, multi-GNSS solution, and the Galileo solution with the improved approach for solar radiation pressure modeling using the so-called hybrid approach. And this figure presents the spectral analysis of the differences in X and Y pole coordinates with respect to the reference model. We may distinguish 2 groups of GNSS-related errors. The first group include the signals at the harmonics of GNSS Draconiti-Gear, and these are the largest for GLONASS, while the differences between both Galileo solutions are rather minor. And orbital resonances. The theoretical periods for the orbital resonances arise from the linear combination of orbit revolution period and Earth rotation period. The main orbital resonances appear at the periods of 3.4 days for Galileo and 3.9 and 7.9 days for GLONASS. When taking different set of n and m terms, shows that we can also expect more orbital resonances in the subdaily domain. So now let's have a look at the high frequency variations in polar motion. And this figure presents the spectral analysis of polar motion series estimated with 2-hour sampling, represented as a complex number. And this figure is limited to the prograde motion only, and the results are different with respect to the reference model. Both GLONASS and Galileo series are visibly affected by the artificial signals at the periods which have been already identified as orbital resonances and indicated in the figure with blue lines. The amplitudes of these orbital resonances may reach up to 30 microarcseconds, and GPS orbital signals coincide with tidal signals at the harmonics of sidereal day, so which makes it difficult to separate both groups. Finally, using all these 3 systems all together reduces the orbital artifacts by up to 60%. When compared the 3-day arcs with 1-day arcs, the 3-day arcs appear right now in color, indicate that using 3-day arcs reduce the amplitudes of orbital artifacts by up to 30%. Based on the 2-hour sampled series of pole coordinates, I have prepared the original GNSS-based empirical models of high-frequency variations in polar motion, including 38 ocean tidal periods. Next, I compared the GNSS-based models with the reference models based on the satellite altimetry and VLBI data. The comparison was made in prograde diurnal band, prograde semi-diurnal band, and retrograde semi-diurnal band. Firstly, the best agreement is obtained for the multi-GNSS solution, and Galileo is the best single system solution, especially for the prograde diurnal band. Finally, the model provided by the SAI-CIBUA is more consistent with GNSS observations than the model recommended in the IRS 2010 conventions. The next result concerns the low frequency variations in length of day, and the figure illustrates the spectral analysis of the differences in LOD, length of day, with respect to the reference model. And we may distinguish three groups of GNSS-related errors: draconitic artifacts and orbital resonances, which have been already identified in the polar motion series, and aliasing of subdaily tidal signals, which appear for all the considered solutions. The figure below presents the differences in the accumulated length of day, which shows the secular drift for GPS, which is up to 16 times higher than for the corresponding Galileo-based solutions. These results refer to the one-day orbital arc solutions. And after extending the orbital arc to 3 days, we may find that most of the orbital artifacts are mitigated, while the secular drift for GPS is reduced when compared to the one-day arc solution, but still remains. Now let's turn to the geocenter motion. And the determination of geocenter coordinates depends on the selected network of stations and quality of station coordinates and the quality of orbit modeling. Using satellite laser ranging to the passive geodetic satellites such as LaGeos is considered the best way to recover the geocenter motion because of stable orbits and well-modeled impact of non-gravitational perturbing forces. On the other hand, measuring geocenter motion using GNSS was always questionable because of the high altitude of the GNSS satellites and high correlations between the estimated geocenter coordinates, especially the Z component, and empirical orbit parameters accounting for direct solar radiation pressure. The next part of the presentation refers to 3 articles. The first one discussed the ability of SLR technique to deliver reference geocenter products, and another 2 discussed the differences in geocenter coordinates delivered from GPS, GLONASS, and Galileo. I will start with SLR technique, and despite the great quality of the orbits for passive geodetic satellites, SLR technique struggles with variable in quality and sparse network of laser stations, and only core sites are considered in datum definition. The figure below presents the time series and spectral analysis of X, Y, and Z geocenter coordinates from 2 SLR-based solutions, which differ in terms of the stations which have been selected for the datum definition. And the selection of datum-defining stations affects the geocenter estimates, and the magnitude of these differences may reach up to 2 millimeters in the amplitude and up to 5 millimeters in the offset between the series. It means that SLR is not perfect, and we have to develop other techniques, including GNSS, aiming to deliver supporting or competitive geocenter products. Now let's get back to the GNSS technique. And this figure presents the correlation coefficients between orbit parameters and geocenter Z coordinate. The orbit parameters include the osculating elements and empirical parameters from the ECOM model. And the correlations are presented for the selected set of Galileo and GLONASS satellites, representing different orbital planes. When all the ECOM parameters are estimated, the correlations are visible at the level of 0.8 for D0 and B1C terms, and 0.4 for D2C term. Reduction of the number of estimated parameters, like in the solutions E1 and E0, makes the geocenter coordinate, Z coordinate, better separable from the orbit parameters. And the reduction of the number of estimated ECOM parameters is possible when used together with a box-wing model in the so-called hybrid solution. This figure presents the time series and spectral analysis of geocenter Z coordinate from GPS, GLONASS, and Galileo, GPS series in blue, GLONASS in red, and Galileo in green, in different approaches for solar radiation pressure modeling and different arc lengths. And when ECOM2 is applied, we see orbital artifacts at the periods of 52 days for GPS and Galileo, 121 days for GLONASS, and the orbital resonances are also more visible, like 3.4 days for Galileo. Please also note the scale change between the GLONASS-based series and the Galileo and the corresponding Galileo and Galileo and GPS series. Using reduced set of ECOM parameters, both with boxwing, mitigates orbital errors but amplifies annual signal. And finally, Geocenter coordinates are not much affected by the arc length. After testing different combinations of GPS, GLONASS, and Galileo constellations, I found the best quality for the GPS plus Galileo solution. And the figure presents the time series and spectral analysis of X, Y, and Z Geocenter coordinates for the GPS plus Galileo solutions, which differ in terms of the applied approach for solar radiation pressure modeling, and this SLR solution as the reference. The presented solutions are in good consistency in phase, but the changes in solar radiation pressure modeling have only minor impact on the X and Y components of the Geocenter vector. Finally, the differences in the amplitude of the annual signal between the GNSS and SLR solutions are significant and may reach up to 5 millimeters in the annual amplitude of for the Z Geocenter coordinate. To sum up, we may identify the relevance of the GPS, GLONASS, and Galileo constellations for deriving Earth rotation parameters and Geocenter coordinates. For the Geocenter motion, the deficiencies in solar radiation pressure modeling have to be mitigated first to improve the GNSS and SLR consistency. GPS is still considered the best for the monitoring of low-frequency polar motion, but using Galileo to the observation of length of day is clearly beneficial to reduce the drift in the parameter. Finally, Galileo shows the best agreement with external models concerning the observation of high-frequency variations in polar motion. The presented results led us to the conclusions. Firstly, GNSS-based geodetic parameters are affected by errors which arise from the orbital resonances, draconitic errors, and tidal signals. And improving the orbit modeling of GNSS satellites leads to a decrease in the influence of orbital signals in geodetic parameters, and metadata on satellite details are particularly useful here. And the best product quality, best agreement with reference models, and least orbital signals is obtained from the multi-GNSS solutions. And the use of Galileo has a positive impact on the quality of the products obtained compared to the GPS-only solutions. Finally, one may pose a question whether the presented results are only valid because of the adopted methodology. And to reject that assumption, I prepared the high-frequency series of station coordinates using precise point positioning technique and independent products delivered by Technical University of Graz. And the figure presents the spectral analysis of differences between the individual solutions, so the solutions delivered from Galileo, GLONASS, multi-GNSS, with respect to the GPS-only solutions. And the signal above 0 means the insertion of system-specific artifacts, while the signals below 0 means reduction of GPS artifacts, so the improvement. And both GLONASS and Galileo solutions are affected by artificial signals, which we have already identified as orbital resonances in the series of Earth rotation parameters and Geocenter coordinates. And using multi-GNSS reduces the orbital artifacts, especially the spuriously large GPS signals at the harmonics of sidereal day. That's the bibliography, and thank you for your attention.